Hello everybody, welcome into another lesson. So today we are going to talk about instantaneous rates of change, tangent lines, and then we'll do a couple of applied problems with instantaneous velocity. So let's start out here by talking about something we talked about earlier in the course. The slope of the secant line to a curve. If you have two points on a curve, you can find the slope of the secant line by just simply taking the second y value minus the first y value, denoted as f of x2 minus f of x1, and then you divide that by the x sub 2 minus x sub 1 itself. That's the traditional slope formula. That is your average rate of change. And we did that earlier in the course when we did the lesson on tangent lines by averaging to secant line slopes. Now what we're looking for is a more direct approach to getting to the slope of a tangent line, which is the instantaneous rate of change at a curve. The idea is that as you get infinitely closer and closer to some point on the curve, the slope of that tangent line, the instantaneous rate of change, is going to be the limit as x approaches a of f of x, the function itself, minus that f of a, that point on the curve, all over x minus a. That is the formula for the slope of the tangent line, the instantaneous rate of change. And we're going to do a few problems here. We're going to find the slope of the tangent line, that instantaneous rate of change, and then we're going to find the equation of the tangent line itself. So let's do some examples of that. Alright, so I have here the equation y equals 1 plus 2x minus x to the third at the point 1, 2. So what we want to do is find the slope of the tangent line at the point 1, 2 on the curve y equals 1 plus 2x minus x to the third, using the definition we just got for the instantaneous rate of change. So here's what we need to do. If we want to find that slope, that instantaneous rate of change, we're going to set this up as m equals the limit as x approaches our a is that x value, that x coordinate of 1. So the limit as x approaches 1 of f of x itself, which is going to be that 1 plus 2x minus x to the third, minus f of a, well, f of a itself is 2, divided by x minus 1. And of course we cannot use direct substitution. We'll get a denominator of 0. But that's okay. We can manipulate this to be able to take the limit. So let's simplify the numerator. This will end up as the limit as x approaches 1 of negative x to the third plus 2x minus 1 all over x minus 1. Well, what I would suggest first, factor out a negative 1 from your numerator. So this would turn into the limit as x approaches 1 of the negative of the quantity of x cubed minus 2x plus 1 divided by x minus 1. Now, if we've done everything right, we should be able to use synthetic division to be able to cancel out an x minus 1. Let's go ahead and do that synthetic division real quick. So let's see, I have x cubed, so that would be a 1. I have 0 for my x squared, a negative 2 for the x to the first, and then a constant term of 1. We'll divide that by 1 for the x minus 1. Bring down the 1, so 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, negative 2 plus 1 is negative 1, 1 times negative 1 is negative 1, 1 minus 1 is 0. So this fits perfectly. So what we should end up getting now is the limit as x approaches 1 of the negative of the quantity of x minus 1 times the quantity of x squared plus x minus 1 divided by x minus 1. And you see how nicely those x minus 1's are going to cancel out. This is just going to now turn into the limit as x approaches 1 of the negative of x squared plus x minus 1. And at this point, we can use direct substitution to find the limit. So if we do that, this would turn into the negative of 1 plus 1 minus 1. So that would give you the negative of 1. That would just give you negative 1 as your slope. So the slope of the tangent line, your instantaneous rate of change at the point 1, 2 of this curve is going to be negative 1. So we found the slope of negative 1. Now what is the equation of the tangent line? This is again from algebra, where you want to use the point slope form of the equation that, let's see, that y minus y sub 1 equals m times x minus x sub 1. Use your point slope form to find the equation of that tangent line. Well, that y sub 1 is 2, so you would take y minus 2 equals your slope of negative 1, or just the negative of x minus 1. So you would get y minus 2 equals negative x plus 1, which would turn into y equals negative x plus 3. So the equation of the tangent line at the point 1, 2, using the slope of negative 1, is going to be y equals negative x plus 3. That would be the equation of the tangent line. And we don't have to bother with finding two separate secant line slopes and then averaging them together. This allows you to go directly to the source. And had I picked a different point on the curve, I would get a different slope and a different tangent line. In the next lesson, when we go into derivatives as a rate of change, we'll actually find different slopes and different tangent lines at different points. So keep that in mind, which this lesson's actually transitioning us into derivatives. Alright, let's do a few more of these so you get a feel for it. Alright, so we have y equals the square root of 2x plus 1 at what point? 4, 3. So we want to find the instantaneous rate of change, or the slope of the tangent line, at the point 4, 3 for y equals 2x plus 1. Then once we find that slope, we need to find the equation of the tangent line to that curve at that point. So once again, what you want to do is set up your limit. So the slope of the tangent line, that instantaneous rate of change, would equal the limit as x approaches your x value of the ordered pair, which would be 4, of your f of x, which in this case is that square root of 2x plus 1, minus that f of a, which is 3, divided by x minus 4. And of course we can't use direct substitution, but what we need to do is the conjugate method. I would go ahead and use the conjugate method. So let's multiply both numerator and denominator by the square root of 2x plus 1 plus 3 all over the square root of 2x plus 1, then plus that 3, and this should simplify rather nicely. This should end up as the limit as x approaches 4 of 4x plus 1 minus 9 all over x minus 4 times the quantity of the square root of 2x plus 1 plus that 3, which should go into then 4x. Wait, why did I say 4x? That should be 2x, excuse me. I knew I was doing something wrong. I was multiplying both 2's. I forgot I was just multiplying a radical. So 2x plus 1 minus 9 would equal 2x minus 8 all over that x minus 4 times that square root of 2x plus 1 plus 3. And I kind of forgot a very important piece, the limit as x approaches 4 of that whole piece. Well, this would simplify into the limit as x approaches 4 of 2 times x minus 4 all over x minus 4 times the square root of 2x plus 1, then plus that 3. Well, notice now your x minus 4's cancel out. This would just turn into the limit as x approaches 4 of 2 all over the square root of 2x plus 1 plus 3. Now we can use direct substitution and find our slope. So this will turn into 2 all over the square root of, let's see, 2 times 4 is 8 plus 1 is 9. Square root of 9 is 3. So 2 over 3 plus 3, which would equal 2 over 6, which would give us a slope of 1/3. So the instantaneous rate of change, or the slope at the point 43 of this curve, is going to be 1/3. Now we just need to find the equation of that tangent line, so we'll take y minus 3, set that equal to our slope of 1/3 times the quantity of x minus 4. Well, that would give us y minus 3 equals 1/3 x minus 4/3. Let's go ahead and simplify this. This would give us y equals 1/3 x. Now negative 4/3 plus 3, well, 3 is 9/3, so this would turn into 1/3 x plus 5/3. So the equation of the tangent line at the point 43 to this curve would be y equals 1/3 x plus 5/3. Let's do a couple more of these, then we'll do some applied problems. All right. We got y equals x minus 1 all over x minus 2. They want us to take the point 32. So we need to find the instantaneous rate of change, or the slope of the tangent line, at the point 32 for y equals x minus 1 divided by x minus 2? Well, in order to do that, let's go ahead and set up our limit formula. So the slope equals the limit as x approaches our value of 3 of this f of x, which is going to be x minus 1 over x minus 2, minus our f of a, which is 2 itself, all over x minus 3. So yes, we're going to end up with a complex fraction. It's not going to be a whole lot of fun, but that's what it is. So let's go ahead and start simplifying. This would end up as the limit as x approaches 3 of x minus 1 minus 2 times the quantity of x minus 2 all over x minus 2, that all over x minus 3. And now let's simplify that numerator sum. This would be still the limit as x approaches 3 of x minus 1 minus 2x plus 4 all over x minus 2 all over x minus 3. Let's simplify a bit further. You end up getting the limit as x approaches 3 of negative x plus 3 all over x minus 2 all over x minus 3. Well, this is starting to come together, because the next step is we're going to take the limit as x approaches 3. That negative x plus 3, we can actually factor out a negative 1. We'll end up getting the negative of x minus 3 all over x minus 2. And then in the denominator, you have x minus 3. A complex fraction, you invert and multiply. This would be times 1 over x minus 3. And now you have your x minus 3's cancel out. This would just turn into the limit as x approaches 3 of negative 1 over x minus 2. And now we can use direct substitution, and we end up getting negative 1 over 3 minus 2, which is negative 1 over 1, or just simply negative 1. So the slope of the tangent line, or the instantaneous rate of change at this point, is negative 1. Now we can go ahead and find the equation of the tangent line. We'll take y minus our y coordinate here of 2, set that equal to our slope of negative 1, which would be the negative of x minus that 3. So you would end up getting y minus 2 equals negative x plus 3, or y equals negative x plus 5. That would end up being the equation of the tangent line at this given point. And I got one more example of this, then we're going to do a couple of applied problems. All right. So let's see, y equals 2x all over x plus 1 quantity squared at the point 0, 0. So we need to find the slope of the tangent line, or the instantaneous rate of change to the curve y equals 2x all over x plus 1 squared at the origin. So let's go ahead and set up our limit formula for the slope. So the slope would equal the limit as x in this case approaches 0 of our f of x. So that would end up being 2x all over that x plus 1 quantity squared divided by, well, x minus 0. Well, all that minus 0 is just that 2x all over x plus 1 squared divided by x minus 0 is simply x. So we actually aren't going to have a whole lot of work to do. We can go right to the complex fraction. This is going to end up being 2x, well, I should say the limit. The limit as x approaches 0 of 2x all over that x plus 1 squared. Now we have a complex fraction, so this would be times 1 over x. Well, you have an x that cancels out. This would just turn into the limit as x approaches 0 of 2 all over x plus 1 squared. Now we can do direct substitution. In the denominator, 0 plus 1 squared, that would just give you 1 squared, which is 1. So you end up getting 2, which is your slope and the instantaneous rate of change at that point. Now we can find the equation of the tangent line. If we take y minus 0, we just get y equals that slope of 2 times the quantity of x minus 0, or simply 2x. So the equation of the tangent line at the origin would end up being y equals 2x. That one actually wasn't quite as bad as it looked. Okay. So now we've seen how to find the slope of a tangent line at a given point, and also find the equation of the tangent line at that given point. Now, let's do a couple of applied problems here, but first we need to talk about instantaneous velocity. So before we found average velocity, which we determined, we know velocity is simply the change in position over time. Your car actually deals with velocity all the time. The difference is between velocity and speed is simply the magnitude of velocity. Velocity gives both a speed and a direction, where speed is just simply the magnitude or the absolute value of that velocity. It doesn't give you the direction. But we found velocity before by taking the average of a couple of average velocities and getting an instantaneous velocity. Well, it works much the same way for instantaneous velocity as it did for what we just did with the tangent lines. So let's see here. Let me grab the book. It might be easier if I hold the book while I write this. If a ball is thrown into the air with a velocity of 40 feet per second, its height in feet after t seconds is given by y equals 40t minus 16t squared. Find the velocity when t equals 2. All right. So let's break this down here. So if a ball is thrown into the air, so picture you're on the ground, you're throwing a ball into the air, and that the velocity that you threw it with is 40 feet per second. Its height in feet after t seconds is given by y equals 40t minus 16t squared. Alright, so what are we going for here? What are we going for? We're not even trying to find the tangent line. We're just simply trying to find the velocity after 2 seconds. So this y equals 40t minus 16t squared, they tell you it's the height in feet after t seconds. T is the amount of time. This function here is the position function. In order to have a velocity, you need to have some movement. You're going to change the position with respect to time. That's all velocity really is. They want you to find the velocity at the time t equals 2. So what we need to do, they tell you that the time is 2. You're basically you want to treat that like your x variable. Only we're dealing with t as opposed to x. Same idea. We just use t with these problems because it denotes the change in position over time. So if t equals 2, why don't we take f of t to find that value for the y position? So for the position itself at the time t equals 2 seconds. So in this case, y is f of t, so let's take f of 2. That would equal 40. Let me separate the problem here. All right, so y equals 40 times 2 minus 16 times 2 squared. Well, that's 16 times 4. That's going to end up equaling 80 minus 64, which would be at 16 feet. So at 2 seconds, we are at 16 feet. It's at 16 feet in the air 2 seconds later. In fact, you could think of this as the point 216 if that helps you. Now, we got the time, we even have the position, we have how high in the air it is. We want to find the velocity at that point. Well, all that is your slope of the tangent line, the instantaneous rate of change at that point. That's your velocity at the time equals 2. So we're going to set this up the exact same way as we did the other problems. So m is going to equal the limit as x approaches 2. That would be our, or I should say t approaches 2. That's our t value of that f of t, which is in this case 40t minus 16t squared minus that f of t value itself, which is 16, all over t minus 2. All right, so there's your limit problem to obtain that. Now, what we need to do is, of course, simplify the numerator. This would turn into the limit as t approaches 2 of negative 16t squared plus 40t minus 16 all over t minus 2. Well, what can we pull out from the numerator to factor out in common? Because the idea is we should hopefully be able to cancel out a t minus 2. That's really what we're going for here. Because as it stands right now, we can't use direct substitution. That's what we're trying to get to. Well, you have negative 16t squared plus 40t minus 16. You can definitely factor out a negative 8, can't you? This would end up turning into the limit as t approaches 2 of negative 8 times the quantity of 2t squared minus 5t plus 2 all over t minus 2. Well, let's see what we can factor in the numerator. This would turn into negative 8. We should definitely have a t minus 2, which I would like to believe would end up giving us a 2t minus 1 all over t minus 2. If I FOIL this, so 2t squared minus t minus 4t, yep, minus 5t plus 2. Perfect. That's just perfect. I should probably say this is the limit as t approaches 2 of this mess. I know I wrote it in the wrong order, but that's okay. Well, your t minus 2's cancel out, so here's what you're going to be left with. You'll have the limit as t approaches 2 of negative 8 times the quantity of 2t minus 1. Now we can do direct substitution. You end up getting negative 8 times, well, 2 times 2 is 4, so that'd be 4 minus 1. That would end up being negative 8 times 3, which would be negative 24. That negative 24 really is going to be feet per second. So at 2 seconds, the ball has a velocity of negative 24 feet per second. Negative, of course, would mean it's on its way down back to the ground. So, and when we get into derivatives, we'll actually be able to talk about the maximum height and all that too, what the maximum height it reaches, but we're not there just yet. But at 2 seconds, the ball has a velocity of negative 24 feet per second, meaning it's on its way down to the ground. Alright, I got one more which we're going to expand upon a little bit further. Alright, so here's this one. I think this one's kind of cool. If an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by h equals 58t minus 0.83 t squared. Find the velocity of the arrow after 1 second. All right. So we're on the moon for this one. If an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by your height function h equals 58t minus 0.83 t squared. They want you to find the velocity of the arrow after 1 second. Well, in order to be able to find that velocity, we need to be able to obtain the height itself at 1 second. So let's take h of 1. Well, that would end up equaling 58 times 1, which would just be 58. And then that minus 0.83 times that 1 squared, which is just 1, you get 58.083, which would give you 57.17 meters. We know the height itself at 1 second is 57.17 meters, so yes, we can call this 157.17. That works. Now, how are we going to find that velocity at 1 second? This is where we're going to get into the instantaneous velocity, so we'll set up our limit. M equals, this would be our h of t, so that would end up being that 58 minus 0.83, or wait a minute, I forgot the variable. 58t minus 0.83 t squared minus that 57.17 all over, I should say m equals the limit, excuse me. M equals the limit, then as t approaches 1, of 58t minus 0.83 t squared minus 57.17 all over t minus 1. This is not going to be pretty, is it? We're probably going to have to bust out the quadratic formula, which I was really hoping we wouldn't have to. No, we should be able to factor out the t minus 1. Gosh, man, this is going to be rough. I'll use synthetic division. I'm not looking for, or not synthetic, I'll use polynomial long division rather. So this should end up giving you the limit as t approaches 1 of negative 0.83 t squared plus 58t minus 57.17 all over t minus 1. Well, let's go ahead here and do our polynomial long division. Sometimes these aren't pretty, but so this is negative 0.83 t squared plus 58t minus 57.17. All that divided by t minus 1. Alright, so t goes into negative 0.83 t squared. That's going to be negative 0.83 t times. So we multiply, you'll end up getting negative 0.83 t squared plus 0.83 t. Now let's subtract. Goodness gracious. So we'll end up having 58 minus 0.8, 58t minus 0.83 t. That would be 57.17 t. Then minus that 57.17. So t goes into 57.17 t. That'd be plus 57.17 times. Sorry, so 57.17 t minus 57.17. Looks like we have no remainder, so this worked. This will turn into the limit as t approaches 1 of t minus 1 times negative 0.83 t plus 57.17 divided by t minus 1. Well, your t minus 1s are going to cancel out, so that made your life a lot easier. So let's see here. So t minus 1s cancel out. Now we can do direct substitution. This would equal negative 0.83 plus 57.17. Let's see what the heck we actually get. Gosh, no. Get 56.34. So the velocity at 1 second is going to be 56.34 meters per second, which means the arrow's still in the air. Even after 1 second, it's still going upward since you have a positive velocity of 56.34 meters per second. Alright, so there are another two parts. When will the arrow hit the moon? So we did the velocity itself at 1 second. The next question is, when will the arrow hit the moon? So let's see. For the same problem, when will the arrow hit the moon? Alright, so when will the arrow hit the moon? If we think about that, that's a height of 0, right? It was in the air and it finally came back down to the surface of the moon. That means the height is 0. So we need to take this height function, set it equal to 0 so we can get that time. So we'll take 58t squared minus 0.8, or 58t minus 0.83t squared, set that equal to 0. We can definitely factor out a t. That'd be t times 58 minus 0.83t would equal 0. Well, yeah, at time 0, if you set t itself equal to 0, that would give you 0. So we're not even interested in that because at 0 seconds we know it's on the moon, right? We haven't launched the arrow yet. What we really are interested in is this 58 minus 0.83t. Set that equal to 0. That'll give us the time from when we launched it to when we get back to the moon. So 58 minus 0.83t equals 0, so 0.83t equals 58. Let's see what we get for t. That's approximately 70 seconds. So it's 69.8795 approximately. We're just going to say 70 seconds. So at 70 seconds, the arrow will hit the moon. So the arrow is in the air for about 70 seconds. So that means at 70 seconds times 70, the height is 0. That's going to come into play for the last part, is what is the velocity when the arrow hits the moon. So we want to find the velocity when the arrow hits the moon. So that velocity is going to be, of course, the slope is equal to the limit as x approaches 70 of our function here, which is going to be 58t minus 0.83t squared minus, that would be, of course, 0, which would just give you this function itself here, all over, and then why did I say x? It should be t approaches 70, all over t minus 70. Well, actually, what we should say is, what did I put in before? We should say as t approaches 58 divided by 0.83. We'll keep the time at 70 seconds. There's a reason I'm keeping this here, because then if I don't change this, we're not going to be able to figure out the exact time or the exact velocity. So t minus 58 over 0.83, well, we could simplify the denominator for once. This would end up turning into the limit as t approaches 58 divided by 0.83 of 0.83t minus 58 all over 0.83. Now, that numerator we can factor out a t. You would end up getting t times 58t, or sorry, t times 58 minus 0.83t. And now I'm sure you're starting to see why I left the time as such. Although for our answer we would say 70 seconds, but for the limit we want to leave it as the exact expression. Otherwise you won't be able to cancel out. So keep those in mind. Now, we have a complex fraction, so this would end up turning into t times 58 minus 0.83t. The limit as, I better write the limit still. We haven't evaluated the limit yet. the limit as t approaches 58 divided by 0.83 of t times that 58 minus 0.83t all over 1 times 0.83 all over 0.83t minus 58. Well, if we look over here, you notice this 0.83t minus 58 in the denominator looks almost like this 58 minus 0.83t in the numerator. If we pull out a negative 1 from 58 minus 0.83t, this would turn into what's in the denominator and they would cancel out. So what you're going to have here is going to be the limit as t approaches that 58 over 0.83, which would be negative 0.83t divided by 1, or just negative 0.83t. Now if you put this in direct substitution, you'll end up getting negative 0.83 times 58 over 0.83. Well, what do you know? You'll end up getting negative 58 meters per second. So the velocity when the arrow hits the moon would end up being negative 58 meters per second, and it hits at about 70 seconds. So those were a couple of applied examples of these problems. Now, in the next lesson, we're going to introduce the actual term derivative, and it's going to be given first as a rate of change. We're basically going to have another formula we can use to find the rate of change, which is more formally called a derivative. So I hope everybody has a great day. Take care.